Hey everyone, it's time for physics. Today we are starting Unit 8, Waves. We're not going to look at any particular sort of wave today, like sound or light. Those are for later units. We're just going to look at waves in general, because the ideas that we learn today, we'll be able to apply to things like sound and light in later units. And as it turns out, we can use the same physics to describe everything from light to sound, to everything from water waves and earthquakes. So first let's start with some formal definitions. So the first definition says that waves are a result of a disturbance that carry information about that disturbance. So let's look at the most simple example. You and your friend are holding on to either end of a rope. So what you're going to do is you're going to flick one end up and down. You're going to cause a disturbance. And that disturbance is going to cause a wave to travel down through the rope. And that wave that's traveling down through the rope is going to carry some sort of information about that disturbance. In this case, the information that's being carried is that, well, there was someone at the other end that flicked the rope up and down. Another example that kind of fits this definition are tsunamis. Tsunamis are giant ocean waves created by earthquakes far out in the ocean. The earthquake causes a disturbance that creates a wave, and that wave is carrying information about that earthquake. So if we study the tsunami, maybe we can figure out something about the disturbance or something about the earthquake. And that kind of brings us to our second definition here. And the second definition says that waves transfer energy or information without transferring matter. Now, if you think about this, this is actually a really powerful idea. If we can somehow transfer energy, or in the form of information, without having to transfer matter, we could do something like, oh, I don't know. We could do something like transfer some sort of energy across the world to our relatives without having to transfer any sort of matter, like a traditional letter or something like that. And now I know what you're thinking. These are exactly like those tin can phones that you perhaps made when you were a kid. What you can do with those tin can phones is you can transfer some sort of energy into the phone, and that energy or information is going to be transferred through the phone. But there was actually no transfer of matter. There was no physical mail being sent. And this is also the basics of how your cell phones work as well. So if we can use waves to describe a bunch of different things, let's figure out what exactly it is that we can measure and describe about them. So the easiest way to figure out all these different things that we can describe about waves is by looking at a water wave. Okay, so I'm going to go ahead and draw a cross-section of a water wave. I'm also, for reference, going to draw a dotted line through the exact center where the water would be resting, let's say if it wasn't windy out that day. So it's the equilibrium position, or where our water naturally wants to rest. So on a windy day, we have these waves that are rolling by. So we look at this and we think, what is one thing that we can measure about these waves? Let's say you're out on the dock fishing and you have a little bobber floating up and down in the water. One thing that we can measure about this wave is what's called the amplitude. The amplitude is simply the distance from the equilibrium position. Okay, be careful, it's not from the very top crest to the very bottom trough, it's just the distance from the equilibrium line to the top of one of the crests or the bottom of the trough. Okay, so the distance from equilibrium. Okay, well, let's look at this too. What's another thing that we might be able to figure out here? Well, we can also measure the distance from one of these crests to another one of these crests. And that distance is what's called the wavelength. And we represent it with the Greek letter lambda. And it looks like this, lambda. Take a second here and draw lambda a few times on your paper, just to get used to it. I like to draw it as kind of like a backwards fancy F and then just a little line on it. Lambda, lambda, lambda. Okay? And lambda we called the wavelength. And that is another distance. That's the distance from one crest to the next. One crest to the next. You could also go from one trough to the next trough. But wait, waves aren't stationary, they also move. And things that move, well, they take time to move. So let's say that we have one of our dock posts sitting in the water here. Well, this wave is moving to the side, it's going that way. And we have a dock post here. One thing that we could count is how many times a wave crest will go past our dock post here. So how many, here's one crest and then the next crest that goes by there. Okay? So how many crests or how many cycles go by in 1 second? Hey, wait a minute, that sounds kind of familiar. That's our old friend frequency. So how many wave crests goes by, how many wave crests will go by our dock post in 1 second? Well, if we have frequency, we also have our period too, and that's going to be just the inverse of that. How many seconds, so number of seconds over 1 cycle. So how many seconds does it take for the wave to move from one crest to the next crest as it's moving by? So the amount of time that it takes for it to go from there to there. Okay, that is our period. Think back to Unit 1 now and remember that, well, we have this, if something is moving, it probably has some sort of velocity. So what we need to do now is develop a velocity equation. Well, remember that we said velocity was some sort of distance divided by some sort of time. Well, if we think about if we want to figure out how fast this wave is moving, we need to figure out a distance. And we know the distance. We define waves by this variable of wavelength. So our distance is actually going to turn into lambda. So we're going to have velocity of the wave, and we have lambda. Okay? But we need to know how many of those lambdas go by in 1 second. And we happen to have another term that we know, frequency, cycles per second. So if we multiply the lambda times frequency, we are going to get the wave velocity. How fast is that wave moving? Okay? Remember that this isn't an equation for how fast is the matter moving in the wave. It's how fast is that information, or how fast that energy is moving in the wave. Now let's quickly do some dimensional analysis here to make sure our units check out. We have lambda is measured in meters, and we have frequency. Remember, frequency is measured in hertz, but that is the same thing as 1 over seconds. So we have meters times 1 over seconds. And if we just multiply these together, just like normal numbers, we get meters per second. So that checks out. Let's talk units briefly here too. Remember that Period is measured in seconds, wavelengths, meters, and amplitude also in meters. Also remember that frequency is 1 over period, and period is 1 over frequency. These are the wave equations that we will be using over the next week. There's one more thing that we need to go over, and that is the two types of waves. It's transverse and longitudinal. And tomorrow, we are going to develop formal definitions for these in class.